Hello, everyone. Welcome back to another video with us here at LMDN STEM Academy. In this video, we will be working through the June 2023 Unit 1, Paper 2. We'll be working through question 2, Part B, which was a question on acid-base equilibria. So for the first part, we have to state the difference between the behavior of a strong acid and a strong base according to the Bronsted-Lowry theory. So according to the Bronsted-Lowry theory, an acid is a proton donor, while a base is a proton acceptor. In an aqueous solution, a strong acid will donate all of its protons, while a strong base will accept all the protons that are available. All right? Part 2 says, write the reaction for the dissociation of ethanoic acid. So when we put ethanoic acid in an aqueous environment, how does it dissociate? So this is the reaction that describes that dissociation. So we have a mole of ethanoic acid in the aqueous state, and then that equilibrates to give us this conjugate base form here, and this proton that gets taken off. So that's how we write that dissociation reaction. And then for part 3, we have to complete table 2. So we have to complete this table below using the variable x to generate expressions for the equilibrium concentrations of the reaction components for a 0.3 molar solution of ethanoic acid. So here's our table. It's an ice table. We have initial, change, and equilibrium. And we have our species here, our components here. And we're told that initially, we have a 0.30 molar solution of ethanoic acid. And initially, we do not yet have any of our conjugate base, and we don't have the proton coming off as yet. So we have 0 in those columns, while we have 0.3 molar for the ethanoic acid itself. And so whenever you're filling out any ice table, the most important thing, or the most important thing to start with, your starting point, should be the presence of your balanced equation that describes that dissociation or that particular equilibrium. And so I've had that populated back here. And so if we're going to use x as our variable, right? Essentially what we're using x as is to denote our change, right? And so let me just grab a pencil here real quick to fill out this, right? So x is, well, let's talk about the balance equation first. It's a 1 to 1 to 1, right? So 1 mole of our ethanoic acid will dissociate into 1 mole of that conjugate base, and we'll get 1 mole of protons coming off. And so if we're using x to denote kind of the change, right, that's taking place, then if this change by x moles, right, and then this will also change by x moles, and then this will also change by x moles, right, because everything is 1 to 1 to 1. And so if I can denote an x here for the change, and I'll just put an x here, and then another x here, and another x here, they're all changing by the exact same amount based on the stoichiometry, okay? So now when I'm at equilibrium now, what will my equilibrium concentrations be, right? And so the equilibrium concentration will be what you started with, minus how much it changed by for the reactant, that is. So my equilibrium concentration will be just that for ethanoic acid. And for these guys, it will be 0, what I started with, plus the change of x, because I'm increasing in these. Remember, I had none initially. So I have to add my x there, and then I do the same thing here, 0 plus x. Okay, so these are our equilibrium concentrations. So let me just box those real quick in a different color. These are our equilibrium concentrations, right? All of these values for each of these species are equilibrium concentrations, and they are going to be the ones that we're going to use in any equilibrium expressions that we might generate for this problem. Okay, so these are our equilibrium expressions. Okay, concentrations. So let us move on. So we need to now generate an expression for Ka, which is the acid dissociation constant and equilibrium constant. We need to generate that for this reaction using the equilibrium expressions that we obtained just now. And so our Ka is generally going to be what? Our products, right? The concentration of our products divided by the concentration of our reactant. And so this was our reactant, these were our products, so that's our Ka expression. And remember, our Ka expression is in terms of equilibrium concentrations, which we just got a while ago. And so for the conjugate base, we knew it was 0 plus X. For the protons, it's 0 plus X as well. And then for the ethanoic acid that we started with, it would have been whatever concentration we started with minus that change of X, okay? And so if we were to simplify this further, we would get that our Ka is equal to X squared, right? So X times X, so X squared divided by the denominator of 0.30 minus X. So that would have been our Ka expression, okay? So moving right along, we're being asked to calculate the pH of a 0.3 molar solution of CH3COOH at 25 degrees C if X is 0.0023. Okay, so all things being equal to what we've been doing, everything that we just expressed and that we just did in our equilibrium table or ice table applies for this particular scenario here. But except now they're giving us the value for X, okay? So we can substitute that in and we'll be good. So they're asking us to find a pH, right? And so the place that we have to start is by saying what the pH is. What's the formula for finding a pH, right? And that would just be that pH is equal to the negative log to the base 10 of your hydrogen ions or your proton concentration, right? And so from part 3, we knew that the H plus concentration ended up just being equal to X, right? Remember, it was just 0 plus X, which is X. And so that's what H plus was. And so if they're telling us that X is now 0.0023, then we know exactly what the concentration of our H plus ions is. And if we know what the concentration of our H plus ions is, then we can just plug that in here, right? Literally just take this and plug it in here. And so hence our pH will then be equal to the negative log to the base 10 of 0.0023, and that will yield us a pH of 2.64. Okay? And so with that, we've come to the end of this question. Consider subscribing to the channel. And if you look here, right, on your left, you will see the next video up. If you look on your right, you will see the Module 2 playlist, where there are tons of other content for you to indulge in and get yourself ready for this exam, okay? Thanks for watching and see you in our next video.